Hello there, everyone. Hello. Namaste. Um, Before I proceed, let me advise you very strongly to use headphones and do not take them off. I am shooting a maths tutorial video. Yes, I'm currently at Mumbai. It is my permanent residence now. Um, you must know something about me as a person because I am going to teach you mathematics. I was schooled in a place called Kharagpur. I think everybody knows about it. Um, that's the place where the first IIT was installed. Thereafter, I did my first year BSc, but I couldn't complete it. It was at St. Xavier's College, Kolkata. I got admission into the engineering college in a place called Suratkal, very close to Udupi. I can now write BE Electrical after my name. Well, that was not enough for me. Okay, so I had to have a postgraduate diploma in education, having studied at the Loyola College of Education. So I was now in a position to teach. I was recruited as a maths teacher in a very distinguished school called the Little Flower School, run by the Sisters of Saint Joseph of Cluny, headquarters in Paris. It was here that my future was laid. I taught mathematics in the school for 30 years, 30, 7th, 8th, 9th and 10th. But my target audience is students of 7 and 8. Why? Why so low? Well, I can't call it low. Well, I've been teaching standard 10 for nearly 30 years and I saw the damage done by poor teaching in standard 7 and 8. These students had a hard time, very hard time, and they had passed the point of no return. I am going to teach you a topic which very few have heard about it also. The textbooks don't give it much weightage, the teachers don't bother about it. Rational numbers. What a boring topic. Boring, but you don't know much about it. What do you know about the rational numbers? Rational numbers, do you know that a rational number can be expressed like this? 3.142857, 3.142857, 1428571, 1428571, 14285, 14285. That is a rational number. Every integer is a rational number. But the converse is not true. There are some rational numbers which are not integers. So that should bother you. That should excite you to learn more, isn't it? I can guarantee anyone who learns under me will not be a mathematics student. Aadmi pagal hai. What does it mean? Be learning maths to be mathematics students? No. You're going to be mathematicians. Yes, that is it. Mathematicians, not mathematics students. Mathematics students anyone can be. But mathematician, this is what the country needs. Every country needs a mathematician, a person who can conceive, deliberate, dig deeper. This is what the country needs. These are the people who will contribute to the economy of the country. You will be clearer about this after you see the ensuing videos. Thank you very much for listening, but please stay tuned for the ensuing videos. Bye everyone. Hello there my friends. I hope you have your headphones on. It's important, don't take it off, okay? Now I'm going to show you the difference between a mathematics student and a mathematician. I shall warn you beforehand. Right now, now let's take an example. There are two figures. See the red lines here? Now your teacher maybe in class 5 or class 6 asked you to bisect the angle formed by these two lines. That is this angle. Now with this OS center and a radius, any radius, cut an arc which cuts this red line at A3. Do not change the radius. With O center and the same radius, draw an arc to cut the other red line at A2. So OA2 and OA3 are equal in length. Now with A2 as center and preferably a larger radius, you can don't keep the same radius, then you get a different figure. With A2 as center and an enlarged radius, draw an arc. Okay. Then with A3 as center and the same radius, don't change the radius. Draw another arc to cut the former arc at A4. So in short, A2, A4 and A3, A4 are equal. Then you joined A4 and O and you found that these two angles were equal. That's where the classroom education stops and the children see it's equal and they are happy. Arey kya teacher hai yaar, oh, very good teacher. You're just a mathematics student. Now let's see what it takes to be a mathematician. Look at this triangle O, A2, A4, the striped triangle. And look at the dotted triangle O, A3, A4. These two triangles are congruent by SSS. Now if you have not studied congruency, it doesn't matter. All I want you is to get the trend of my argument. So these two triangles, the striped one and the dotted one, are congruent. Therefore this angle is equal to this angle. You can also use another argument. O, A2, A4 and A3 forms what is called a kite. It's a very popular geometrical figure, not given much importance in the classroom. One of the features of kite, it's a kite, okay? Did I mention that? The longer diagonal of a kite, this one, always bisects this angle. So I've given you two arguments by which you can prove that the angle is bisected. So that's the procedure for a mathematician. Got it? Yes. So you are now a mathematician. Part 1. Okay? Hello there, students. Do not remove your headphones. This is what again you were taught in standard 5 or 6, but you didn't question. Maybe you were too young that time, okay? Alright, I draw a line, this line of any length. Then with O center and any radius, you draw an arc to cut this line at A, and without changing the radius, you draw an arc to cut the line at B. Therefore, OA is equal to OB. I think you've got that. Now, then with A center and a radius a little more than AO, it has to be more than AO. Please understand that, okay? You draw an arc. Then with B center and the same radius, don't change. You draw another arc to cut the former arc at P. Join PO. PO is perpendicular to AB and you are very, very happy. Mathematics student. Now let's make you a mathematician. AO is equal to OB. In triangles PAO and PBO, sorry. AO is equal to OB. AP is equal to PB. PO is common, therefore these two triangles PAO and PBO are congruent. Therefore this angle which is opposite AP and this angle which is opposite PB are equal because they are opposite equal sides. Therefore 2 theta is 180 because this is a straight line. These are adjacent angles on a straight line. Therefore theta is 90. Now you are a mathematician. I hope you got that. Okay, so now you know the difference between a mathematics student and a mathematician. Okay, a mathematician dives into the assignment and finds out more details. Okay, yes, yeah, keep tuned. Headphones on, please. Yes, now we are inching slowly but surely towards our destination. You must be wondering, when the hell are we going to deal with rational numbers? Hold on, man, hold on. Yeah, suppose you go for athletics training, they won't put you on the track right away. You'll have to do some freehand exercises to develop your lung capacity, your calf muscles, your thigh muscles. So these are just warm-up exercises, okay? Now, have you ever tried counting the number of strands of hair on your head? No way, that's insane. Because you'll reach a number that you cannot count, you cannot measure it, okay? That is, this number is called infinity, unreachable number which you cannot measure. If I asked you to calculate the number of drops of water in a cup, you'll go insane, you won't be able to do it. So that's called, this number, unreachable number which you cannot measure, is called infinity. That's the title. Now have a look at these numbers. There are 1, 2, 3, 4, 5, 6 fractions. Have a look at the numbers in black. In all the numerators, 20, 20, they are the same. Now have a look at the denominators. What is your observation? You should be seeing it by now. The denominators are steadily decreasing. 20, 10, 5, 1, 0.30 is 1, 0.60 is 1. Now, I hope if your decimals are not intact, better go through it, okay? Because I'm sure you'll understand these quotients 1, 2, 4, 20. But that's not important. Seeing the quotients is not important. What is happening to the quotients? The quotients are increasing. Look at this one. This is 0.30 is 1. That is 1 by 10 to the power of 3. So 10 to the power of 3 goes up. So 20 into 10 to the power of 3 or 2 into 10 to the power of 4. The same case, you figure this out for yourself. Oh, okay, I will do it. 0.60 is 1 divided by 10 to the power of 7, or 20 into 10 to the power of 7, or 2 into 10 to the power of 8. Got it? Now, if I have not reached 0, so you can imagine if I reach 0, 0.00000000001. It'll be 210 to the power of, I don't know what, you will reach trillions, you will reach something you cannot measure. Okay, so in short, infinity, any number divided by 0 is infinity. This is the focus of this lesson. Any number divided by 0 is infinity. But be careful, the converse, 0 by any number is 0. 0 by any number, 0 by 2, 0 by 5, 0 by 20, 0 by 30, all these are 0. But 20 by 0, 30 by 0, 40 by 0, this is infinity. Got it? I think it's clear, right? Okay. Yeah, now we come to what is known as the number system. Can you see the trend? We are slowly getting to rational numbers. Look at this number 3b. Don't pay attention to that. Actually, these are videos which are numbered. The first one is my speech, which is video number 1, not mentioned. Then the others are, there were 2 for mathematicians, 2a, 2b. Then the one you just saw was 3a. This is 3b. Okay, it follows that fashion. You know natural numbers, 1, 2, 3 up to infinity. Okay. Whole numbers, the same except you have a 0. Can you see the 0? Here, the 0 there. Now we come to something a little different. Can you see in red, -3, -2, -1, 0? I will see these are negative natural numbers. Then you have the 0. Then you have the 1, 2, 3, 4 positive natural numbers going to infinity and plus infinity. These go to minus infinity. Now, these numbers, the whole negative series, the positive series, and the 0 form what is called the set of integers This is z plus z. This is the symbol for integers. Okay. Now, so in short, the purpose of this video is to tell you what integers are. Okay. So integers comprise z negative, z positive, and 0. That's all about. This is a very short video. Okay, so I hope you understood it. This is the full setup. Okay. Well, what do we have here? Now we're coming to our manzil, rational numbers. So this is what you're waiting for. Yeah, your wait is over. Rational numbers. Now remember these things about rational numbers. Definition. It's a fraction. This is easy to remember because rational comes from the word ratio. What else? The numerator and the denominator both belong to the set of integers. This you must be knowing. It comes in set language. It doesn't matter. This simply means it belongs. These numerator and denominator belong to the set of integers. The denominator is not 0 for reasons already mentioned. Okay. So this is important. The denominator should not be 0. Now look at all these integers. -4, -3, etc. These are all integers which you already know. Now look at this. Each integer can be a fraction. -4 is -8, but it can be -16 by -4. So each of these can be expressed as a fraction. Can you see that? Now 0, be careful of 0. 0 by any number is 0. Okay? +1 is 6 by 6. 3, 24 by 8. So we come to the conclusion that all integers are rational numbers. This is important. It is true in all conditions. All integers are rational numbers. Got that? Hello there. Please don't forget to use your headphones. Well, this is a further progress on rational numbers. All rational numbers are not integers. If you see the previous file, we mentioned that all integers are rational numbers, but the converse is not true, huh? All rational numbers are not integers. Before we show that, first let us acquaint you with the symbols. The symbols use numerators n, denominator d. Now 1/3 is 0.3333. This is called a recurring decimal. We shorten it by writing 0.3 and a dot on top. Now they'll repeat not only in ones, in groups of 2 also. See, 1 by 11 is 0.09, 0.09090909. So we write 09 and we write a stroke if it's more than one number repeating. Similarly here, 22 by 110, 101. Look at this. 21782. 1782 repeats. So that's why I wrote here 0.2. At 1782 there's a bar. NT means non-terminating. So have a look at the symbols once again before I proceed. It's important, okay? This is file 4A, as you can see. Okay? Yes. Well, let's see how rational numbers behave under different conditions. All these 1/3. See, this is case 1. Numerator less than the denominator. Then we also have numerator more than the denominator. Patience, patience, you will see that later. Right now, only focus on the numerator less than the denominator. I hope you will agree that all these are rational numbers. Why? Both numerator and denominator belong to the set of integers. The denominator is not 0, so these are all rational numbers. Now, if you work it out in a decimal form, yes, you'll get 0.33333 repeating in groups of 1, repeating in groups of 2. 123 by 999 is 0.12312312. 3 by 7, 428571. All these are not integers. What are we discussing? Whether rational numbers are integers or not. See, all these rational numbers, they are not integers. To make it in simple form, integers are rounded off numbers, okay? So I hope this is clear so far. This is case 1, please note. Where the numerator is less than the denominator. So if the numerator is less than the denominator, you don't get rational numbers, but you certainly get recurring decimals. Okay? There's no two ways about it. You have to get recurring decimals, okay? Okay, let's get ready for the next part, where the numerator is more than the denominator. Okay? Well, are we ready now? Yeah, now we come to case 2, which is the numerator more. It's more than the denominator. Here there's some confusion. Have a look at it first. In all cases, the numerator is more than the denominator, as you can see. 22 is greater than 6, 22 greater than 8, 16 greater than... this is a mistake here. Excuse me, pardon me. Then 20 by 10. 24 by 3, 30 by 5. So I repeat, don't consider 16 by 100. Yeah, this stands for terminating decimals, this stands for recurring decimals, this stands for integer, yes or no. Now 22 by 6 stands for, you'll get 3.66666. It's a recurring decimal, so it's not a full number, therefore it's not an integer. Similarly, 22 by 8. 2.75, it's a terminating decimal but not an integer. Similar, then let's go to the red numbers, okay? 20 by 10, again numerator more than the denominator, you get 2, but this is an integer, yes. 24 by 3, 30 by 5, you get a whole number, so yes, they're integers. So in the case of numerator greater than the denominator, we cannot say, okay, we have to examine it. So some cases yes, some cases no. Got that? But if the numerator is less than the denominator, as we saw in 4b, if the numerator is less than the denominator, then it cannot under any circumstances be an integer. But over here you have to examine it, you have to be careful. Okay? Have you got that? Yes, now we come to 4d. I hope you're keeping track of the numbers. It's not important, but sometimes for reference we need it. Observations. Yeah, I hope you know what an observation is. Observations are something which you observe. Then after the observations, you come to the conclusion. But this is before the conclusion. You can see it's a conclusion combined. Observations and conclusions go together. So if n is less than d, there's no integer at all, though you don't have to worry. You have to worry here if n is greater than d. If numerator is greater than the denominator, may be or may not. See file 4c. In 4c is clearly shown. This is 4c. You can see which is terminating, which is recurring. Okay. So this is important to read this. In all cases 1 and 2, we saw case 1 was where the numerator was less than the denominator, case 2 where n was greater than d. So in decimal form, or q is rational number, falls into two types. Q is a rational number, please note. It falls into two types. Now suppose you take 3 by 5, it's a rational number, but the numerator is less than the denominator, so it cannot be an integer. Okay, Now if you take 1 by 3, that also cannot be an integer, but you get 0.333333. So recurring, when you get a recurring decimals, it is definitely, surely, positively a rational number. So rational numbers come under two types: recurring and non-terminating. Then type 2, terminating. See case 2 and 4c. I should have mentioned that. Terminating is case 2 and 4c. So suppose 8 by 5. If you have 8 by 5, 1.6, it's a terminating decimal, but it's a rational number. So rational numbers in decimal form come in. So you might get fractions, that's easy to recognize. The purpose of this is to recognize rational numbers in whatever form. So in decimal form, they come in only two types. That's to our advantage. Okay. So the first is recurring. Okay. 10 by 3. 3.3333. 10 by 5 are integers. The denominator is not 0, but you get 3.33, etc. repeating. So it's a non-terminating. Repeating means it's understood as non-terminating. Type 2 is terminating. See case 2, file 4c. So I hope that is clear to you. Alright. Well, this is the next video. The title is The Emergence of Pi. You might have seen this. Well, if you haven't, it doesn't matter. Pai is pronounced pi. We think we Indians are very proud of mathematical prowess, ability, foresight, expertise. But these people, who are these people? Egyptians, Babylonians. Who are these guys? Now, these people had, I don't know if they were employed or they had any job, a 9-to-5 job. Obviously, they were not employed because they had a lot of time. What they did is, see, suppose you have a wire in the form of a circle. Open up the wire and make it a straight line. Measure the length of the straight line. Do you know that the length of the straight line is the circumference? Fine, then you're smart. And before doing that, they measured the diameter. Now they found that for any circle, the circumference by the diameter was a constant. We shall call it A. This constant, we'll call it A, okay? Imagine this. You take any circle, big, small, medium, measure the circumference, measure the diameter, take the ratio. It is a constant, okay? This constant is 3.14644660942. We are calling it A. Now, I told you earlier that rational numbers can only come in two forms. But does this conform to any of those forms? It's repeating? No. It's terminating? No. Therefore, this is not a rational number. It's an irrational number. Now, it's so sad. You made a sensational discovery, and what was wrong? It's sad. This number was an irrational number. With an irrational number, you can't do a thing. Mathematics can't proceed. You can't do any further calculations. So that's why I wrote here. Sad to say, this discovery was marred by the fact that A is an irrational number. But see, when you want to invent something, you have to have an indomitable spirit. You can't give up. So these people didn't give up. So let's see what happens on the next slide, okay? Hello there, my friends. We are almost come to the end. In fact, this is the last slide, okay? This video is 5B. Now it's written there from video A, 5A. A was equal to 3.146. This value you have already, okay? This is an irrational number. This was what was causing all the problem. So it had to be abandoned for obvious reasons. Now, these people were not the type to give up. Okay? I think they were not employed in any. They didn't have a regular job, so they had a lot of time. And now these people, they thought among themselves, uh, let's convert this to a rational number. So they experimented with a fraction, all the types of fractions. Okay, since this number a was 3 point something, it was more than 1, so the numerator had to be more than the denominator. So after trying and trying and trying, I don't know how many times they tried, 22 by 7, okay, they hit upon a number 22 by 7, I'm calling it B. It was a suitable replacement for A for two reasons. It is an irrational number. Sorry, I'm very sorry. It is a rational number. 22 and 7 both belong to integers. 7 is not 0. Secondly, it had a value very close to A. See, 3.142857. It's actually 3.142857, 142857, 142857, 142857. It goes on and on. So it's a recurring decimal, but it is a rational number. And the value is 22 by 7. This was symbolized by the letter pi. The symbol pi. This was a very historic achievement because even now we take the circumference of a circle as pi d. The area of a circle is pi r squared. Pi is used in many places, okay? So hats off to this gentleman who has given us this legacy, okay? Alright, so this is the last of it. Let's have a little rounding off, alright? Okay. Yeah, are you happy that the video is over? Yeah, it's quite tiring, you know. I hope you understood what was taught. Now, if you did not understand, it's quite possible. You can contact me on Facebook for now. Once I am sure that the response is good, I will get you on my WhatsApp. I will devise ways and means for you to get in touch with me. But right now, Facebook, you're all on Facebook, so obviously you can get in touch with me. Now, if you want to be a good mathematician or very good in mathematics, first, you must be good in geometrical drawing. Now, what's the connection? Now, suppose you're drawing a figure and the length is twice the breadth. It must look twice the breadth. Suppose the length and breadth are in the ratio 7:3. 7:3 means the length is a little more than twice. If you have to draw an angle of 60 degrees, make it look like 60 degrees. You need not use a protractor. See, the more accurate the drawing, the better your chances of solving it. I'm talking of geometry. Geometry is the part of mathematics which I love. Yeah. There's another very dangerous mindset among the students. If you find that you cannot do a problem immediately, you think that you are not fit for mathematics. No, don't compare yourself to some of the people who are gifted. No, you can be good in mathematics. Okay? You can develop your intelligence. It is possible. So if you find that you are struggling with a problem, don't think that you are no good at mathematics. No, even we teachers get problems. Sometimes we cannot do. We have to spend sometimes an hour or two, sometimes some days. Okay, so don't get these things out of your system. I have taught you some essential things like what it is to be a mathematician. It's the attitude that is important. A good mathematician has the right attitude, and don't give up. Have that habit of what is called tenacity. Don't give up. Just go on trying and trying and trying. Even if you take 2 hours, 3 hours to figure out a problem, it's not time wasted. Believe me, it's not time wasted. No, you've learned something for life. So wish you all the best, mathematicians. You can always get in touch with me on Facebook. Okay. Bye for now, and thanks for listening.